Our first talk is Stefano Olla, heat equation from deterministic dynamics.
Thank you, Pablo. Thank you, Ana Jacinta, Maria Joao, Gunther, Patricia. Great that you keep organizing this conference, and I say it every time, but I think that's a great initiative, and I can see only as parallel the one that Joe Leibovitz organized in Rutgers. I will be there with it's now 92, it will be the 155 edition. So you should do it twice a year to be competitive. But once a year is fine. But when you will be 92 and it will be the 60th, I will be dust in the dust. But you will keep going on, and I think the great initiative. This conference that keep us together, people in analysis of PDE and probabilist in interacting particle system. So this is a recent work that I've done with Carlangelo Liverani, who has been a guest here. I think gave a lecture in the edition of 3 years ago. I'm sorry about the people that already heard this talk, Patricia, Francois, and someone else heard this already, so they can fall asleep. I don't. So this probably the people who were here at that time when Carlangelo talking, they was developing these techniques about fast-slow dynamics, and this is a further development from there. I learned a lot of dynamical systems from him, and when we really applied these dynamical system techniques to obtain heat equation from a complete deterministic dynamics. Basically, the idea is that to show that the deterministic Hamiltonian dynamics, when perturbed with a deterministic dynamic that is enough chaotic, behaves like a stochastic dynamics, the typical stochastic dynamics that have been working most of my career. They just show that these stochastic dynamics are quite justified if you see it as emerging from microscopic chaotic dynamics on a different scale. So let's see what the problem is. That this is the heat equation in its full nonlinear terms. The one we will work on will be the linear one. So Kt, the thermal conductivity, this temperature, and that's the way the temperature evolves in a macroscopic space-time diffusive scale, and Ct is the specific heat. We want to see it more as a conservative law for the energy, so we should write it here with the diffusivity, which is the thermal diffusivity, which is what we call D of E. So the dream basically is how to obtain emerging in a diffusive space-time scaling out of a microscopic dynamics, typically an Hamiltonian dynamics of particles, where they move a particle, a position Qi and Pi, velocity Pi or momentum Pi, so it's the mass, and this Hamiltonian system where the Hamiltonian is HQP. Let's put ourselves in a most simple situation. We have one chain, a Fermi-Pascal type. There is a pinning potential, there is an interaction between the particles, and X is the site in each potential of where the particle. So Qx will be the displacement of the particle X out of an equilibrium position, that is, let's say, 0. So the dynamics as the Hamiltonian dynamics as energy conserved. Among many other conservation laws, but the energy is conserved, and the current of the energy is just this one. Just compute the time derivative of the energy. The energy per particle is given by the kinetic energy, and the potential energy, the pinning potential, and the energy of the interaction. We just arbitrarily assume that the energy is the interaction with the particle on the left. Here. And then you look at the distribution of the energy as a distribution in space, and you rescale time like epsilon minus 2. Epsilon here is just a parameter, small parameter, and you see the test function G is rescaled on the space by epsilon x. So this is a diffusive scaling of space and time, and you expect that in the macroscopic limit, you converge to the solution of the heat equation, where the diffusivity is given by the Green-Kubo formula, which is a space-time variance of the current in equilibrium when resistant for an infinite system, which is at equilibrium with energy E. There's a Gibbs measure associated with this. There's a certain temperature corresponding to the energy and so on. So you see that the thermal diffusivity is a variant. So there is behind this limit a central limit theorem, a space-time central limit theorem, which you have to prove somehow in non-equilibrium. Okay, so this is a dream, and in fact, we don't even know about it. For a complete deterministic system, we don't even know if the thermal conductivity converge. And we have done a lot of work, also with Frederic Bernardin, on stochastic perturbation. For example, if you flip randomly the velocity, if you change the velocity random way, then at least you can prove that Green-Kubo formula is well defined and converge. But but in general, we don't know, even for stochastic dynamics, we don't know how to prove heat equation for the energy. And basically, all the techniques we know that are based, good powerful techniques based on relative entropy, they don't work for energy. They don't work for energy because the relative entropy is already relative with respect to Gibbs measure to a certain energy and controls only the second moment. So you need a little bit more than second moment. And this is one of the problems that plugs the thermodynamic limits. It's something I've done in my head many times. We like to control higher moments, and energy is just.
Stefano, you are saying that when you're referring to the stochastic dynamics, is the dynamics in which you add this energy conserving noise?
Yes, yes. For example, you flip the velocity, the sign of the velocity. This obviously converge. This conserve the energy, conserve the kinetic energy, don't touch the position, so conserve the total energy. But destroy all the other integral of the motion besides the energy. Okay. The energy, the only one left over.
And you cannot prove the dynamic limit for this?
Not in the nonlinear case. For the linear case, we see yes, but not for the nonlinear cases. But you can at least prove that the thermal diffusivity is well defined, that the formula converge. This is a work with the trick of many years ago. So if we take the system harmonic, then the macroscopic equation is going to be linear, and then we can prove something. Just we can prove the heat equation just out of techniques that we show here. But at least for stochastic dynamics. But what we want to deal here, and this is something we've been discussing with Carlangelo many times, in 30 years probably, how to obtain it from a deterministic dynamics. So this is the harmonic dynamics I was taking before. This is a discrete Laplacian, and there is a pinning potential. So the black part is completely the harmonic dynamics I was talking before. And then instead to put noise, we put some deterministic chaotic perturbation, which is as following. There is an f, theta could be an angle or a point in a torus, and f is a chaotic map, is accelerated by epsilon minus 1, so it's somehow accelerated. We take now the system just finite, so the system is made by n particles and put periodic boundary condition, so to make it as simple as possible. And then the velocity, there is, okay, the particles have now 2 degrees of freedom. So Qx and Px you have to consider like there are 2, so that each particle has and now beside the Hamiltonian dynamics, I rotate the velocity with a chaotic map. The 2 components of the velocity get rotated, so the J here is the matrix 0, 1, minus 1, 0. You can take any other rotation matrix, that's going to be fine. And F this chaotic map, and B is the function in these angles. And then we have to speed up somehow. This, you see, this is going to be fast. And you have to speed up fast enough. So speed up fast enough looks a bit like a noise. It's not a noise, but it looks like a noise. And actually you have to speed up like n to the a with a bigger than 6. And yes, this chaotic map has an invariant measure. F is the chaotic map as an invariant measure, and B of theta should be of 0 average respect to the invariant measure. Okay. So this is kind of a magnetic field, an external magnetic field that rotates the velocity, and it's deterministic.
Stefano, could you comment again what's theta?
Okay, theta is here explained. Okay, can take two cases. I mean, actually, this article is, we find the article in the archive now, and we developed the case where F is a smooth map on the interval with chaotic, says the first derivative has to be bigger than lambda, strictly bigger than 1. So this is just a map on the interval, chaotic map on the interval. So, dynamical system, people can do absolutely continuous invariant measure, which you call rho star theta, and you have exponential decay of correlation, central limit.
Stefano, how do you choose the initial point of the
that's very important, the initial condition, absolutely. Then more interesting is to use an Aharonov map, because this is time reversible. Well, the first one is not time reversible. If we perturb it with the Aharonov map, it's time reversible. Technique-wise, a bit more complicated proof, but things work out well also for an Aharonov map of in the torus with the function. So that makes the total dynamics completely time reversible. Time reversible in the sense of dynamical system. There still exists a unique invariant measure, and you have an exponential decay of correlation. Okay, so this is dynamics, and because of this characteristic dynamic, you know that there is a central limit, there is a condition on B that assure that you have a central limit theorem with the variance for B, which is strictly bigger than 0. We call this variance gamma, and this parameter gamma will be very important because will appear in the macroscopic equation. So this is just, I mean, if you just look at this map, they have this central limit theorem. These are running fast, and so there is some central limit theorem that is happening for them with this variance here. And then you have, in fact, convergence is a central limit theorem. This, if you have invariant principle, also if you rescale properly, you converge to being a process with variance gamma. Okay, so this is well known, this part here. And okay, these are the assumptions of the initial distribution. The initial distribution at this point becomes incredibly important because this is a deterministic system. But some randomness has to be in the system, and randomness all comes from the initial distribution. And actually, you can choose for P and Q something deterministic. It's not important. But the angles, we must have some random distribution with some absolute continuity part. Could be very, very small, but some absolute continuity part. The condition is the following. So you start with the distribution of the position and velocities, condition and the angles, This could be also deterministic, I don't care. But the distribution of the angles, of all the angles, we have now n angles, has to be absolutely continuous with this density. And you have a condition of the density. So this is kind of important. As we see, you have some, of course we do this for some iteration in time, and you start with something random, and the whole technique is to be sure that after a certain time, which is a certain scale, you still have some randomness. You are not losing this. Otherwise, if you arrive to something that is deterministic, condition and position, then you are stuck. So you have to maintain this randomness in time. This is where the important point. Okay, so you have, of course, to assume that you have an initial profile. So in the limit, you must have a microscopic profile. That will be the initial profile for the heat equation. And then the limit theorem is the following. We have the convergence in expectation of to the solution of the heat equation. The diffusivity is d over gamma. The initial profile is the one that we established to be. And the diffusivity d is explicitly computable, depend on the pinning omega 0. You can see that when omega 0 goes to 0, this is 1, which is the case, unpinned case. The unpinned case is more difficult because there is another conservation law, which is the volume, which will also be a diffusivity. We can deal with that, but that's a more complicated story that I'm not talking now. So this is a theorem. As you see, unfortunately, it's only an expectation. So it would be nice to have a theorem which says that improbability or most surely, and then eventually take almost surely initial condition respect to the initial measure. My old advisor, Joe Leibovitz, insists a lot on this sense, but the techniques only allow to to obtain an expectation. For the reason I said before, we don't have control on higher moments. We only control second moments. Energy depends on the second moment. And if you want to go to a low large number, you need a little bit more than second moment. And the only thing you can control is relative entropy, and cannot help with that. That's a thing that we plan. But at least we can obtain this theorem that we have. And for the people who likes control, yes.
So the method to prove this limit theorem is via relative entropy?
We don't use relative entropy.
Ah.
Not at all. It's totally useless.
So what do you use to prove this?
Well.
Stefano?
Yes.
So similar questions, like when you always say decay of correlations, so you have the mixing condition.
These maps are mixing. This is well known.
Quantitatively, quantitatively, like the mixing rates are known, etc.
Oh, they have all kinds of infinitely functional pieces. Yeah, and that is one of the things that we can use techniques that control very well the central limit theorem in finite time, so that we can control the error. That's very important. Yeah. That's why we can couple the fastness, the speeding up of the chaotic map with n, which is the dynamic limit parameter. So we're just taking one limit. One could take two limits, make converge first to random dynamics. I will explain. So this is an error that you can also control the error respect to the limit, and will depend on this alpha. There's some control on it. So there is an equivalent stochastic dynamics. So basically the idea is the following: the system behaves like it was this random system where there is the same dynamics, microscopic dynamics here, but instead of the chaotic map, there is this stochastic perturbation right and right. This is So Wx are Wiener processes, that is like in a circle, and there is a Wiener process in a circle that is mixing up the two components of the velocities, and each particle has this. That's what it is. And for this system, we know how to prove hydrodynamic limit. Basically, you go on and you have Ito formulas and so on. And what we have to prove is that somehow you are close enough to this system. But we don't want to prove the convergence of the system. That will require much stronger conditions. We want just to prove that the covariance, the structure of the covariances are close, because that's all we need to control in order to obtain the dynamic limit. So we have for this system the same equation. For people like Stratonovich, this is written that way. I don't like Stratonovich. I don't know the configurations. But anyway, that's exactly you obtain exactly. But you see, the gamma that you see here in the capta is exactly the central limit theorem variance that you see from the maps. Okay, so the strategy of the proof. Okay, suppose you are just working with random dynamics. Then you do the usual thing, you just look how energy evolves in time. You have the current, you have a first derivative, you can put it here, and you have some small mistakes. Then you have to control the current. The current is what? Is Qx times, no, Px times Qx plus 1 minus Qx. So the minus is here. So you have to control this time integral of this covariance. So basically, if you know how to control covariances, limit of the covariance, you can close the equation. Unfortunately, this stochastic dynamics is closed. The dynamics of the covariance of the stochastic dynamics is closed. So there is a lot of algebra to compute, but you can go on. And in fact, so this the matrix of the time integral of the variance. This is don't need to control the variance, just a scalar product between Qx and Qx prime, or Px and Qx prime, and so on. So you have these matrices, and you just write down the evolution, and you see that there is some algebra, and you go on compute. Linear relations, so you go in Fourier transform, and eventually you close the equation. So that's something that you don't need relative entropy, it's just you go by explicit calculation, controlling errors. Of course, you have errors when integrating time that has been controlled. So this is a generator of the random evolution. There is A is the generator of the Hamiltonian dynamics, and this second order term is the random evolution. And gamma is what was coming there. So for the random evolution, in fact, you control the variance. This is the way you control the variance. You just look at the generator applied to second order polynomials, and you have that you get something small, and say basically something of order n. This is what you do for the stochastic dynamics. For the deterministic dynamics, you want to show the same thing, but the error that you do, because now you're using the stochastic, the deterministic dynamics instead of the stochastic one, but you want still to use the generator of the stochastic dynamics, you have to prove that it's kind of small. And how much time do we have? 6 minutes. Okay. The natural idea is to take the interval in time, the microscopic interval in time, divide it in time in the interval of time h, which has to be long enough that the maps do their work, but short enough that the particles don't move too much. And you have to control this. And you have to do it in such a way that after this step, you still have some randomness and you can start again with your maps. Otherwise, you're stuck, as you said before. And the mathematical tool control this is called standard pair. These were ideas developed more recently by Dolgopiad, but the ideas go probably back to Sinai, to let's say Young, and so on. Are measured on the angles which are delta function, very, very close to a delta function, but such that still the dynamics evolves deterministically. I mean, the point is that you can start even in equilibrium, with the maps in equilibrium, but then at the evolve, and you condition the position at the time h, you may find, you're not in equilibrium anymore. we are conditioning the position. So you have to be sure that once you condition the position, the angles still have some absolute continuity. That's the main point that you have to control. And okay, I'm not going to describe this with the technical, but the point is to associate the function g, which the function of the angles, that the angles associate to a configuration, that when the angle moves a little, the configuration could move even less. Okay, I'm not. And after, so there are this distribution of the angles, which are called standard pair, and they are where you control the absolute continuity of this density. And the point that after this time h, you still have not a standard pair, but a convex combination of standard pairs, which have the same parameters, the same kind of smoothness, the same kind of initial condition, and that allows you to restart. And then you go on like that, and nothing works out. Here at the standard pair. So last thing I want to at least keep about entropy, I want to say about something about entropy. And, but basically, I mean, we apply this technique for the equation, but I think can be applied for many other problems we have been studying all these years with stochastic dynamics, like, for example, obtaining the compressible Orry system of equation in the hyperbolic scaling. This is where you can prove the ergodicity. Basically, instead to put noise, we can put this such maps. The equilibrium fluctuation, maybe super diffusive fraction evolution, all these things that we have developed for stochastic dynamics. I think we could use this technique to obtain it from the deterministic. Okay, so.
Thank you, Stefano. Very nice talk. Any question?
So I had a question, like, so in your method of proof, like the limitation is more at the level of the estimates in chaotic like dynamics, or at the comparison, or I mean, so if you wanted like to do, I mean, for example, n to the power 6 or such thing.
Yeah, okay. We took n to the power 6. We have to split it up. Maybe working much more, we can n to the power 3, but you have to speed up somehow. The ideal case would be not to speed up, just that the hydrodynamic scaling would work together, like, but it would be like putting some anharmonicity in the dynamics that should do the same work. For this, we will need some different techniques. No, certainly, this is the technique is really based on the fact that there is something fast and something slow.
The limitation is more at the level of so the estimate in mixing and ergodic theory, that these things are very hard. So that's the limitation for you.
Yeah, but there are very clever people that work all these years, and they have very good control of this system. The point was to use this standard pair to use these techniques. Standard pair were already used, but never in a system that where the dimension was growing. Like there is a paper by Carlangelo, Liverani, and Piat, where they obtain this kind of diffusive, the one you were talking about, the interacting Brownian diffusion, no, conservative of the energy. Yes, they obtain it from, and they use, but the dimension of the system is fixed. Here, the point that the dimension of the system is growing.
Okay. Any other question?
So, could you approximate some Hamiltonian dynamic by some sequence of maps? Like, for example, we create some maps that we can approximate a Hamiltonian dynamic.
Sorry?
So,
Approximate Hamiltonian dynamics with deterministic
so you
maps.
said that you can do even reversible, but not Hamiltonian.
Okay, yes, no. No, this, I mean, I said that these are magnetic fields, but they are kind of a stereomagnetic field. We don't consider the energy of the magnetic field. So the dynamic is deterministic. It's even time reversible, but it's not Hamiltonian. I don't know how to do it.
No,
So as far as I understood, like you compare the paths of like this E2 SPE with the ODE that you had to prove the missile. This was sort of the idea.
Sorry, I don't understand.
So as far as I understood, the idea to prove the result was to compare the stochastic differential equation with the ODE that you proposed.
Come the time integral of the covariance. So we don't really prove that our dynamics converge to the stochastic dynamics. That will require speeding up much faster than that. But we don't care. We want to obtain the heat equation. We only need to show that the time integral of the covariance of the dynamic of the stochastic dynamics and the thermodynamics are somehow close.
Okay, so you had terms that sort of mimic the Brownian motion, and in your ODE, you had terms that should mimic the effect of the Brownian motion in the SDE.
Yes.
And this was in one dimension.
Yes, each map is one dimension, but also in the stochastic dynamics there are one dimensional Brownian motion. Yes.
Okay, and the heat equation was also then one dimensional in the end.
The
The heat equation that you.
Oh, that doesn't matter. Those two dimensions do not have anything to do with each other.
Okay.
We can do it on, we do it in one dimension for simplicity, but you can be in a lattice, d-dimensional lattice, that really doesn't matter. The important thing that you have at least 2 degrees of freedom for each particle, because you want to rotate, put noise in the velocities, and rotate the velocities. So like obtain this noise on the velocities, like flipping the sign of the curve randomly. We don't want to do it randomly, but we need some space.
You said you don't have an Hamiltonian dynamics, you have an external field, but you want them to replace it with the interaction with the body that has mass flow in its end, like a huge body that's basically acting as an external field. You cannot change the dynamics of the big body because it has big mass. So it's almost
These are exterior fields.
But
These are kind of random, not random, these are chaotic exterior fields, yes.
But can't you replace an external field with a Hamiltonian interaction with a massive body?
I don't know, because if you have to do that, if you want to do the Hamiltonian in a Hamiltonian way, then there will be the energy of these maps that you have to take into account. That will complicate the problem. Plus, something that bugs dynamical system is that they like maps at discrete time. They don't like continuous time, even though one could put negative curvature dynamics to each particle. I don't know, maybe there is a way to do that. I'm learning these things. I'm not dynamical systems. I'm learning now a lot of dynamical systems, thanks to Carlangelo, but
Okay, we don't have time for more questions. Thank you. Sorry for those that wanted.